Hello, everyone. This is Cassie Lu. I'm working for Intel Networking Platform Group. Chenbo, would you like to introduce yourself?
Hello everyone, I'm Chenbo from Intel.
Okay, today, Chenbo and I will talk about device virtualization or emulation in DPDK. And actually, we are now proposing this feature to community. Let's start with motivation and background. As we know, QEMU is the de facto host for device emulation. And the device emulation is usually monolithic emulation, except one use case, and that's high performance device emulation. In that case, device emulation is still in QEMU, and DPDK provides data path acceleration. In addition, QEMU community is now doing multi-process QEMU or disaggregated QEMU design for reducing attack surface. Disaggregating IO serves from QEMU is their starting point. In order to support that, VFIO-user protocol is proposed. The protocol allows a device emulation in a separate process out of QEMU. In response to QEMU change, we propose DPDK not only provides data path acceleration, but also host high-performance device emulation. With this in mind, we come up with a modular device emulation framework in DPDK. So we now understand the motivation and background. Let's have a look of an example of emulated device setup. In this example, there are two processes. One is QEMU process. The other one is device emulation process. In the emulated device setup, both QEMU commands and DPDK commands are involved. From QEMU commands, we can see that the assigned device is linked to remote process. Actually, here remote process is a device emulation process. For remote process, it has socket address information. Since QEMU process needs to use sockets to communicate with device emulation process. In the device emulation process, DPDK command will be used to create two kinds of device. The first one is device emulation. The second one is data path provider. As you can see, the device emulation also has the socket address information. Since device emulation process also need to communicate with the QEMU process. With respect to data path provider, it needs to be bundled into a specific emulation device emulation, which the data path provider wants to provide data path. Okay, from this example, we get some feeling of how QEMU and DPDK work together to achieve the emulated device setup. But what's the exact things behind this example? I think the device emulation solution overview might give you some hint. So this picture shows the device emulation solution overview. At the left-hand high side, it shows the QEMU process. At the right-hand side, it shows device emulation process with DPDK library. In the QEMU, it has VFIO device object. QEMU uses it to represent device to VM. In the emulation process, it has device emulation and data path provider. Both device emulation and data path provider are attached to the dev bus. In our current proposal, the relationship between VFIO device object, device emulation, and data path provider are one-to-one. In addition, VFIO device object in the QEMU needs to use VFIO-user client to encapsulate requests coming from guest drive into VFIO-user protocol and communicate with VFIO-user server. And finally, get an action for request done in the device emulation. So we introduce VFIO-user library into DPDK. This VFIO-user library provides VFIO-user server implementation. Meanwhile, we introduce emulation dev library. This library introduces a new device type called emulation dev. This type is for device emulation to be abstracted as. So from the whole solution, we can see the VFIO-user library and emulation dev library enable DPDK to be an alternative I/O device emulation library. That's pretty much from my side. Now I would like to hand over to Chenbo.
Okay, let me share my desktop.
Chenbo, you can start. I can see your screen now.
Okay. Yeah, for now, I will show you guys how to build your emulated device. And to build your own emulated device, you have to build up two main components here. The first component is device emulation, and the second component is data path provider. The device emulation is built up with two libraries. The first library, RT VFIO-user library, and RT emudev library. The RT VFIO-user library will act as a VFIO-user server here, and you can see in the figure that VFIO-user has a client. Potentially, it could be a QEMU, and a server. It could be a DPDK, and VFIO-user and VFIO-user client and VFIO-user server will communicate using the VFIO-user protocol, and the QEMU as a VFIO-user client will use VFIO-user protocol to get the device information from the server and configure the device. And the RTE emudev library it's for abstracting the device emulation as an emudev device. The emudev device will expose a set of APIs for use, and the second component here, data path provider. It could be any type of device driver, and here we will use EtherDev for an example, and it will be similar to any device EtherDev PMD and DPDK, and the only difference is that it will use emudev APIs here. And first, I will introduce the first component here, the device emulation, and it will consist of two parts. First, how this VFIO-user protocol looks like, and the second part, how to make your device emulation fits into the EmuDev framework. Okay, as I said that VFIO-user server in DPDK, VFIO RT VFIO-user library acts as a VFIO server in VFIO-user protocol. So I will just introduce a VFIO-user protocol here. And we are very familiar with the VFIO. VFIO has its own abstraction for a device. For example, VFIO device has some regions and IRQs. And take a PCI device for an example. A VFIO PCI device has regions like bar regions, config space regions, and normally a VFIO application use syscalls like IO control, read write, and mmap to interact with the device in kernel. And so the only difference between VFIO-user and kernel VFIO is that syscalls are replaced with VFIO-user protocol messages over a Unix domain socket. So a VFIO-user application has all the VFIO primitives, and it will use a Unix domain socket to interact with a device, emulated device in user space, like DPDK process. And since I have said that it will use a Unix domain socket, there will be a client and a server. Client could be QEMU, and the server could be DPDK process. And the client QEMU will send a set of messages to get the device information and configure the device and set up the memory DMA memory table. And let's take a VFIO region for an example. So how does QEMU set up a VFIO region? First, it will send a will send a message named VFIO-user device getting for to get the device information, which includes the region number, and it will send another message called the VFIO-user device get region info to get a certain region's information. And if the region is unmappable, the server will not only respond with the region information and also respond with the memory FD of the region. So the client QEMU will just mmap the region with memory FD, and then it can access the region, use virtual address here. And if the VFIO region is not unmappable, the QEMU will use another set of messages to access it. The messages are VFIO-user region read and VFIO-user region write. The slow pass region read write will also help QEMU access the region. And so you can see the server should prepare all the device information and receive the request from client. Like DMA map unmap, and the server will maintain the DMA table here. And also sometimes it will also send some requests to a client. For example, the slow pass DMA read write and a slow pass interrupt. Okay. So after I introduce the VFIO-user protocol, and let me introduce another library here, the RT EmuDev library. First, I will introduce the EmuDev device object. How does an EmuDev device object looks like? And you can see in the figure that EmuDev device object has three main parts. three main parts, and the first part is regions. Regions are sorry, regions are device layout, and it is exposed to the device data path provider. And each device could have its own device layout, and the regions could be mapped to the device memory of the device, and the data path provider could use the regions to access to receive some data path related control command from the device emulation, and also set some information into the device emulation. And the second part, the queues. The queues includes the address and size, which will be used to locate the queues. And the doorbells, it is for the guest driver to notify the data path provider. And interrupt is for the data path provider to notify the guest driver. And you can look at the structure definition here. It shows a specific implementation. And the device information will also contain the region number and the max queue number. And this is the third part here is the memory table. The device emulation will also maintain the DMA memory table, and it will offer a handle and some helper function for the data path provider. Then data path provider will use the handle and help function for address translation. So these are three main part of the EmuDev device object, and besides this, the EmuDev should have its own device ops for application or data path provider to core. So now I will show you how this EmuDev device ops looks like, and before introducing the specific ops, we should first have a sense that those ops have two types. First, the first type is for application to core, and the second type is for data path provider to core. And let's look at the five categories of the device ops. First, the lifecycle related ops. It includes like device start, device stop, device configure, and device close. So these ops will be called by application for lifecycle management. And the second category, notify ops, the subscribe event, unsubscribe event. Those ops are for both application and data path provider to call. They will register some event callback when the device emulation makes some event. It will use a callback to handle them. And the third category of ops is region related. As I have said, that the EmuDev have some regions. You have two ways to access the region. First is region map. You can memory map the whole region and directly rewrite it. And another way is a more fine-grained way. Instead of taking over the whole region, you can get or set attribute of a certain region. So those ops are both for application and data path provider. For application part, that it will just configure and set the regions, and the data path provider, it will simply get some attributes or rewrite the region and the QOps. The QOps is for data path provider to get some queue information. The queue info will include the address and size, and RQ information, doorbell information, uh, and the data path provider will use it to set up queues. And the final category, DMA ops. It is for data path provider to set up DMA table. It will just get DMA memory table from the device emulation, and it will for a high performance implementation, it could get a handle and use some helper function provided by the device emulation. So that later it will use the handle and the helper function to do address translation. Okay, and until now, I think you guys have a rough idea of how to build the first component emulation, device emulation, using the to introduce the libraries. And now I will introduce the data path, the second component, data path provider, and it is an EtherDev PMD, and it will use Emulate APIs and apps provided by device emulation, which I have just introduced. Okay. So here's an example of how to build up your data path provider and EtherDev PMD. In device probe, in driver probe, and you can first get the device information to query the device info, and the device information will contain the like device type, the region number, and the queue number. And in probe, you should first check the device type is the correct type that your driver could drive, and then you can do a region map and memory map a certain region, and then you can just rewrite it, and also you will get some attributes, and just read the device attributes in the regions. And after probe, when you do the EtherDev configure, you will get queue related information, like queuing for doorbell info, IRQ info, and use them to set up the queues. And also you will set up your DMA table. Like I said, get a handle and use some help function to do address translation in your data path. And also in the EtherDev start, you will subscribe some event. That's for data path that's for the EtherDev PMD to register some event callback to emulate device. For example, the event could be a device reset or a device destroy, some events like that. Okay, now I have introduced how to build up your emulate device yourself, and we would like to share that our status and plan. First, the VFIO-user protocol that I have introduced is RFC patch. It's already in the QEMU mail list, and you can check it with the link. And me and Cassie and I have sent the DPDK RFC patch. The RFC patch includes the two libraries that I have already introduced. and you can check with this link. And our next steps will be to submit our RFC v2 patch. The v2 patch will include v1 revision, of course, and a first emulated device in DPDK using our device model, using our device. And your feedback and comments welcomed. And if you have any questions and some new ideas, you can just contact us with those emails. Our email address are listed here. So do you guys have any question for us?
Hi, Chenbo. I see a question from Gauri Shankar. Is there any performance comparison with VIOS and Virtualized?
Okay. Cassie, would you like to answer? And I will answer if the performance about the performance against VirtIO host. I think the performance is based on mainly based on the ring how to design the ring. The VirtIO ring is decided by the VirtIO spec, but if you implement your own device, the device rings is decided by your own device spec. So we have to do some tests. It may have better performance than VirtIO. We're using our own device, but it depends on the device, I think.
Yeah, actually, here we just introduce a framework, but as performance as is concerned, it depends on the specific device you want to emulate it. Okay, I see one question. What device you want to emulate? Currently, we try to in the next release we will have a NIC network interface card as to emulate.
Okay,
And Thomas, yeah.
Please go ahead.
Is it time?
Yeah, it's time.
Yeah. I saw that Thomas has. Yeah, I saw that Thomas said maybe we don't need device emulation at all. Yes, I think yes. If the client is based on the QEMU, I think we have to need it. But if the client is not QEMU, we may need a device. We may don't need the device emulation at all. Yes, I think.
Yeah, so you also based on that, so you introduce a modular design there. So we separate device emulation and data path provider. So the data path provider standalone could work with no device emulation for container case.
Okay, I think the next session starts. So I think that's all for our session here. Thank you guys.
Thank you.
Thank you guys. Bye.